Imagine you're standing inside a building the size of a football stadium. Somewhere behind thick concrete walls, something is splitting apart atoms smaller than you can imagine. That process is about to boil water, and that boiling water is about to power your entire city. Sounds strange? It should, because at its core, a nuclear reactor is just an incredibly complicated way to boil water. Here's the part that surprises most people. A nuclear power plant doesn't work that differently from a coal plant. Both heat water into steam. Steam spins a turbine, the turbine spins a generator. The generator makes electricity, that's it. The only real difference is what's doing the heating. Coal burns fuel with fire. A nuclear reactor splits atoms with a chain reaction. And splitting one tiny atom releases millions of times more energy than burning it ever could. So, how do you actually split an atom? You need a very specific kind of material. Most reactors use uranium, specifically an isotope called uranium 235. Isotopes are just versions of an element with slightly different weights. Uranium 235 is special because its nucleus is unstable enough to split apart when struck by a neutron. When it splits, something remarkable happens. It releases energy, it releases radiation, and it releases more neutrons. Those new neutrons go on to strike other uranium atoms. Those atoms split too and release more neutrons. This is called a chain reaction, and once it starts, it can sustain itself. But here's the thing. If left completely uncontrolled, that chain reaction would spiral out faster and faster, generating dangerous amounts of heat almost instantly. Engineers had to figure out how to control something that wants to multiply exponentially. Their solution involves two key components: moderators and control rods. A moderator, usually water, slows down the neutrons flying around inside the reactor. Slower neutrons are actually more likely to split uranium atoms, which keeps the chain reaction steady rather than chaotic. Control rods do the opposite job. Made of materials like boron or cadmium, they absorb neutrons rather than letting them hit more uranium. Slide the control rods deeper into the reactor core, and you absorb more neutrons, slowing the reaction down. Pull them out, and the reaction speeds up. It's essentially a dial for how much energy the reactor produces at any given moment. Now, picture the full setup. Deep inside the reactor core sit thousands of uranium fuel rods, arranged in a tightly packed grid. Around them flows water, acting as both moderator and coolant. As the chain reaction proceeds, that water heats up dramatically, reaching temperatures over 300 degrees Celsius. In a pressurized water reactor, the most common design in the world, this superheated water is kept under intense pressure so it doesn't boil. Instead, it flows into a separate chamber called a steam generator, where it heats a second, completely separate loop of water. That second loop is the one that actually turns to steam. Why go through the trouble of two separate loops? Radiation. The water that touches the fuel rods becomes radioactive. Keeping it sealed in its own loop means the steam that spins the turbine, the part of the system open to maintenance and airflow, never comes into contact with radioactive material. It's an elegant solution to a genuinely tricky problem. That steam then rushes through a turbine, an enormous set of angled blades built to spin under pressure. As steam forces the blades to turn, that mechanical motion drives a generator, which uses spinning magnets inside coils of wire to produce electric current. This is the exact same principle Michael Faraday discovered back in 1831 with electromagnetic induction. It's the same idea used in wind turbines, hydroelectric dams, and coal plants. Nuclear power isn't inventing a new way to make electricity. It's just using an extraordinarily powerful heat source to do it. What makes nuclear energy so efficient comes down to raw numbers. 1 kilogram of uranium can produce roughly as much energy as 2 million kilograms of coal. That's the power of splitting atoms instead of burning molecules. It's part of why, according to the International Atomic Energy Agency, nuclear power currently supplies about 10% of the world's electricity, despite relatively few plants operating worldwide compared to fossil fuel stations. Here's a common misconception worth clearing up. Many people picture the thick white plumes rising from cooling towers and assume that's dangerous smoke or radioactive steam escaping into the air. It isn't. Those towers aren't part of the nuclear process at all. They're simply releasing excess heat by evaporating ordinary water, the same way steam rises off a hot shower. What you're looking at is just water vapor, not radiation. Another misconception involves the idea that reactors could explode like a nuclear bomb. They can't. Weapons-grade uranium is enriched far beyond what power plants use, to levels reactors simply don't reach. The uranium fuel in a typical reactor is only enriched to around 3 to 5%, nowhere near what's required to sustain a runaway nuclear explosion. So the next time you flip on a light switch, consider what might be happening behind the scenes. Somewhere, water is being superheated by atoms splitting apart in a carefully controlled chain reaction. Steam is spinning a turbine. A generator is converting motion into electricity. And it all traces back to a discovery made over a century ago, refined into one of the most efficient power sources humanity has ever built. It's not magic. It's controlled, deliberate physics, engineered down to the smallest detail. And now you know exactly how it works.